So, today we will start the new session on event detection. Event detection, it is it's a phenomena what we can tell it is comparable with say the fact that we have a room and there is some activities going in the room, and what is going inside, if the doors are not open and we are not in the room, we can actually look through the window and get that what is going on. So, similarly, within the body a lot of physiological activities are going on all the time, a lot of activities are going on, and we want to actually notice them in a non-invasive way. That means, we do not want to go inside or insert any sensor inside, but we want to observe that what is going on, how it is going on, and for that we take the help of the biomedical signals, because biomedical signals, they are associated with these physiological changes. So, if we have the good idea about the process, so from that biomedical signals we can actually get that how these physiological activities are going on, at what stage they are. So, from that idea about that process and from the information about that biomedical signal, we can get that. If we take an example, we can tell that if there is a fire in the room, how we can get that? That we can see the flame, through the flame we can get that the fire is there inside the room. Okay. Same way, if we get actually heat wave, that the heat is spreading, then we can get that there must be some source of fire, otherwise from where the heat will come. So, even if we cannot see that actually flame. So, these two are associated with the fire. So, from that knowledge we can infer that there is a fire and we can take the appropriate action to distinguish the fire in the room. So, same way here through that biomedical signals we can get actually that what is going inside the human body, and the word event is associated with that fact that all the physiological activity it does not give any clear signal. So, whenever it is giving a clear signal that we call as an event. Okay. So, we will go through different examples, then these meanings will be more clear to you. So, let us first take one such system, that is the cardiovascular system. In fact, if we look at this system, it is nothing but a circulatory system, it is circulating the blood throughout the body. What we have here, that we have the main thing is the pump, that there is a heart here which has actually 4 chambers, that we can say 1, 2, 3, 4. Okay. These 4 chambers, the upper chambers, they are the atria. So, for the right upper chamber, that we get the blood, oxygenated blood from the lung, and it is discharged to that lower ventricle, that lower atria, it is discharging the blood to the lower ventricle. Lower ventricle is responsible for actually distributing the blood throughout the body from toe to the head, and as it gets distributed through the different arteries, it reaches to the different branches and that the smaller blood vessels. So, those at the end it goes to the capillaries and reaches each of the cell, and from each of that capillaries there, that the cells actually they give the the carbon dioxide rich blood, and that again is collected by the capillaries, and they are collected accumulated in the veins, and they come back to the right upper chamber, that is the right atrium. And right atrium, the sole job is to collect that blood, it gives it to the right ventricle, that is the chamber number 3 we have marked. From there it goes to the lung. Lung actually helps for the exchange of that oxygen from the air to the blood and release of the carbon dioxide from the blood to the air, and the oxygenated blood that comes to the left atrium. So, this is the circulation going on, and we are interested in it because that if this actually activity gets disturbed, then all our cells, they would actually be deprived of the oxygen, and if they are deprived of the oxygen, they will not be able to release the energy, which is very essential for any metabolic activity. And they will first, when they starve of oxygen, they will not be able to get actually the energy, and they will start dying. Okay. And that is why you will get that that a person, if he cannot actually heart stops for some time, that person may be revived, but the patient, the doctors actually diagnose that kind of person as brain dead. That means, by the time the brain cells have actually stopped working, they have died. So, even if you see that the heart is going on and the patient has revived, got back the life, but he will not be able to do anything. Okay. So, here so it is a very major actually that activity, and for that we should be very careful about actually this, how this activity is going on. So, look at that it is going in a proper way, and we will go through the different stages of it and the signal associated with it. For the cardiovascular system, the signal associated with it is the ECG signal. Now, for the ECG signal, first what we get, that is the P wave. So, let us recall that how the ECG wave looks like, that the overall signal could be like this. This is the P wave, okay. And so, first part we are looking at. So, P wave, it is actually started by a node or a set of actually the cells which gives a electrical impulse. Okay. There, that is called SA node. SA node actually is a lead in this, but there are more cells or more nodes as nearby the SA node, who also helps SA node to strengthen that signal. Now, as soon as the SA node gives a signal which acts as a stimulus to the muscles, that the upper two chambers or atriums, they start actually the contraction. However, here in this actually image we show the dashed line that is showing the propagation of that signal, but in this that atrium there is no special set of nerves to carry this signal. So, this spread is slow, and that is why the contraction takes place slowly, and this this P wave, which is associated with that contraction of the muscle, that is a slow waveform with about 80 millisecond the time span. Okay. If you look at the time span, that the P, that is the time we will get, and it has a small amplitude, that about 0.1 to 0.2 millivolt, and especially it is small when we compare with the QRS complex. Okay. However, if you compare with the other signals like EEG or so, which are at microvolt level, then you would feel that no, P wave is also have a lot of strength. So, that is the first actually that the part or first event, and what it signifies? It signifies the atriums have started contracting, and what is associated with it as it is getting actually contracted or they are contracting, there are some valves in between the left atrium to that left ventricle, same way for the right ventricle to right that atrium. So, these valves they open because of the pressure, and the blood starts actually getting released from the atrium to the ventricles, from the left atrium to left ventricle, right atrium to right ventricle. Okay. So, that activity is started. So, we get that from that ECG signal or the P wave of the ECG signal. Now, let us look that what is next. Next is we get the PQ segment. That means that the signal we have seen that PQ RST, here is the P Q. So, in between that from P to Q. So, there is a time lag between the P wave and that QRS complex or the starting point of the QRS complex. Now, that time is actually that you can say the gap between the two events, and that in this period what happens, as the contraction has happened for the atrium, the blood actually flows from that atrium to the ventricle, and here is a node called AV node, which has a very interesting job. It acts as a register that it simply takes the signal and arrays that signal for some time. Just like in a computer program we have a NOP operation, we add a delay, same way AV node actually arrays that signal. It does not allow it to decay also, that and it just delays that signal, and the basic motivation for that at that moment if that signal it goes to the ventricle also will start contraction, and that will actually deter or upset the process of the transfer of the blood from the atrium to the ventricle. So, at that moment it is desirable that the ventricles should be relaxed, they should allow the blood to flow. So, for that AV node stops that signal, and that helps for the transfer of the blood. And because there is no electrical activity, that if you look at after the P wave is completed, then there is actually it is almost going through the isoelectric line. So, there is no activity or special signature we can get. So, it is called as a non-event phenomena. Okay. So, and this is about again of the same actually time period as the P wave, that is 80 millisecond. And this helps actually to get this baseline, okay, that isoelectric line what we are talking about, this actually helps to find that where is that baseline of the ECG, that we are aware about that the baseline drift. So, there it is important to know the baseline, that whether any baseline drift is there. So, it helps to get that. Okay. So, this PQ that segment, though it is a non-event phenomena, it is very important, because the blood unless it is completely transferred to the ventricle, then in the next actually part the ventricles will not be able to actually distribute it throughout the body. Okay. For that is true for the left ventricle, and for the right ventricle, that it need to send it to the lung. So, that part will not take place properly unless the transfer of blood is complete. So, that way though that this non-event phenomena is important. Now, let us go for the next part, that is the most important part, that is QRS complex. So, if we take this, look at the sketch of that P, Q, R, S, T. So, in this QRS is having the maximum amount of energy, and that it has actually the maximum not only energy, that the whole signal because of the that amplitude and the speed we get, that is the most important event. Okay. So, that so we need to look at that the QRS complex. Now, after the PQ that part that is over, that when the QRS actually will start, when the AV node will release actually the signal, this AV node will release the signal and allows it to go to the ventricle. When it allows to go there in the ventricle, then what happens that there is a number of nerves in the ventricle. First is that bundle of His, which carries the signal in the first part, then it has the two branches, that right bundle branch and the left bundle branch. They helps to actually distribute the signal in the two respective ventricles, and then there are smaller actually nerve fibers called the Purkinje fibers. They helps to take that signal to all parts of the ventricle. Now, as the signal comes through these nerves and the speed of the signal is much higher in the that when it moves through the nerve fiber, that signal comes almost instantaneously to all parts of the ventricle, and all the muscles, they start the contraction together. So, this simultaneous this contraction, that gives rise to a huge pressure, and the corresponding that signal that comes as a QRS complex, which is actually a very sharp and tall waveform, and that that it's also have a duration 80 to 100 milliseconds. So, if you look at the duration is not actually smaller than the PQ or that P wave, but because of the amplitude or the strength of it, it looks actually the change is much sharper and sudden. If you look at that magnitude compared to the P wave, it is about 5 times higher. It is 1 millivolt actually signal we get here. So, after that, as it contracts, actually what is the physiological activity? It happens that as the ventricles start the contraction, so far the valves in between the atrium and the ventricles, which were allowing the flow of the blood from the atrium to the ventricles, they will get closed. So, the transfer of the blood from the atrium to the ventricles will stop, and that increase in pressure, that will open the valves in between the ventricles and the arteries. So, the arteries, they will actually, that as the valves will open, they will start actually carrying the blood outside the heart. Okay. So, that is the main activity associated with the QRS complex. Now, let us look at the next part of it, that ST segment. ST segment, it's again a non-event actually phenomena, because there is no such electrical special signal. So, it is a plateau, it again gives the isoelectric line, and in this period actually what happens that the ventricles remains contracted, and as it remains contracted, that the flow of the blood from the ventricle through the arteries, that will continue. From the right ventricle it will go to the that lung, and from the left ventricle it will get distributed throughout the body. So, that is the way it actually helps to distribute the blood in the body. And the duration, if we look at that, it is actually that that segment duration is about 100 to 120 millisecond, and that if we have some kind of disease like myocardial ischemia or infarction, it may actually cause any change in this ST segment. What will happen, instead of a isoelectric line, it may get elevated or it may get depressed. Okay. So, there would be a change, it will not remain as a horizontal line anymore. So, that gives an idea about what is the state of the heart or the health of the heart. Okay. So, this segment is important, so that the transfer of the blood from the ventricle to the lung and to the body takes place, we get sufficient time for the transfer of the blood. Okay. So, that is the main purpose of this ST segment. Now, let us look at the next part, that is the T wave. In the T wave, what happens that the muscles in the previous case actually were contracted, that is because of that depolarization of the muscle cells. Now, the repolarization happens, and as the repolarization happens, they get relaxed, and that relaxation, that means that the pressure inside the ventricles will come down, and that because of that the valves actually which were allowing the flow of the blood from the ventricle to the arteries, they will get closed down, and the blood transfer from the ventricle or the supply will be cut off by that. And this relaxation, it is associated with the T wave, the relaxation of the ventricles, that what we get here, that the T wave signifies that relaxation of the ventricles, and again that it does not actually show anything more than that it is the time for the closure of the valve. And here if you look at the time duration again it is about 120 to 160 millisecond. The amplitude is low, that 0.1 to 0.3 millivolts. So, about we can say P wave, sometimes a little more, sometimes is low. If it is low, it is difficult to detect, and there is a long duration of it. So, that is about the T wave, and this T wave, if you look at that what happened to the relaxation of the atria, that was taking place. The only thing, it was taking place with that the contraction of the ventricle. So, that relaxation of the atria, that is not actually becoming apparent in the form of a signal. Even if there is a signal which is very weak, that gets actually subdued or masked by the much stronger signal, that is the QRS complex or the contraction of that ventricles. Now, if we ask that why that some of the signals they are strong, some of them they are weak, the reason is that if we look at the walls of the atrium, we see the walls are much thinner there. On the other hand, the ventricular walls are much thicker. Now, what that signifies is there are a lot of more muscles in the ventricles. and because of that because of the presence of large number of that muscles, and they are simultaneous actually action because of the presence of the network of the nerves, the signal given by the ventricles, that is much stronger, whether we talk about the contraction of it or the relaxation of it. Okay. So, that is why we see that that QRS complex or the T they are in a sense actually much stronger than the P, and the relaxation of the atrium, that is actually occurring simultaneously with the time of the QRS complex, and we are unable to get it separately. So, we stop here and start with a new topic in the next session.